We've determined how to solve oblique triangles using the law of sines with two of the different circumstances, where we were typically given two angles and one other side. But now in situations where we're given side-side angle, oftentimes we're unclear whether or not there's a triangle in the first place. And even if there is, sometimes there's multiple solutions. There's two solutions. So we're going to look at something referred to as the ambiguous case of the law of sines. In this diagram, let's assume that we were given angle A and side B and side A. If we were given those particular values, then we would have a full ratio of angle A and side A with some other random side. Now, if angle A was this particular, if side A was this particular side over here, notice that the side of this triangle would be the longest side between A and B. A would be greater than B in this case. But the problem with this is that what if A was much shorter? A could be so short that it never even reaches the other side. So there's certain times where A is significantly less than B, or the opposite side of the angle given is smaller than the other side, and therefore it's just like a pendulum and it'll never actually touch. The first time this would ever touch is if it touches at a 90-degree angle. So in this situation right here, if this happened to be a 90-degree angle, then we would notice that there would only be one solution. But we just saw a situation as well where there could be no solutions if A is too short. So if A happens to be too short, there could be zero solutions. But it could be that A is a particular size where it might actually be this length, but let's just assume that we were given the length of A to be that length right there. The problem with this is that there could also be another triangle if we allow that opposite side with that same length to pull away from angle B or away from angle A as opposed to closer to angle A. So notice that in this situation, if we were given side A, we don't know whether side A comes back towards angle A or if it goes away from it. Therefore, there's two different potential situations there, or two different triangles. So you could have a situation where there are two solutions. This is why we refer to this situation as the ambiguous case. Ambiguous means unclear, or we can't tell one way or the other what type of triangle we have until we actually go through the work. So again, let's say that angle or side A was this length. Well, that would mean that side A could be coming back over here to be the exact same length. So in this situation, we would have two potential triangles. This really thin one right here, or this really large one right here. So in this situation where we're given two sides and the opposite angle of one of them, this is referred to as the ambiguous case, and we're going to see how to deal with that when the time comes. Now we know that we have the situation side-side angle if we're ever given an angle here with its opposite side, and then some other random side is given. So in a situation like that, the best way to do this is to draw the diagram and say, well, angle 55 is going to be or an angle of 55 degrees is approximately this angle. Now I know that side B is going to be somewhere over here, right? So typically the way that we like to do this is to label this side as the other side given. Let's say side A. And we'll say that that is 25.1. Now, if we're going to be 8.94, think about that. That's about a third of the distance here. 8.94, somewhere around there, right? 9 times 3 would be 27. So about that would be the length that we're looking for. So notice that we should be able to recognize just by drawing this that no matter where I draw that length of about 8.94 for side B, that's never going to make it. It's never going to make it to the base of this triangle. So we can already see just by drawing it that there's no solution. There's no such triangle. But I'd like to take you through the process of the law of sines to demonstrate how we can tell that there's no triangle simply by applying the law. So let's say that sine of angle A over its opposite side, which is 25.1, is equal to sine of angle B, which is 55 degrees, over its opposite side, which is 8.94. So now if we cross multiply, we end up getting that sine of angle A is equal to 25.1 times all of this ratio, sine of 55 degrees over 8.94. So now notice that this is a bit different than what we'd seen previously with the law of sines, because by the time we cross multiplied, we were often finding another side. But now we should realize that what we're solving for here is sine of angle A. So then we're going to have to take sine inverse in order to find what angle A is going to be. So when we simplify this ratio over here, our value ends up becoming 2.29986. And so now we're trying to find when does sine of some angle equal 2.299. But we should realize real quickly that that's impossible. Since remember that sine of theta is somewhere between 1 and -1. So we could never have sine of an angle becoming anything larger than 1, and therefore there's no such angle that makes this true, which is how we knew at this point that there is in fact no such triangle. So if you try to draw it and it appears that there's not going to be a triangle, the process of using the law of sines demonstrates for sure that you were right. Let's take a look at another example. Now in this example, we should recognize that we're given angle A and its opposite side. So we draw this angle of about 55.3 degrees, and we realize that side A is going to have to be opposite angle A. And so side B is going to be this length right here. So if side B is 24.9, then what we should recognize is 22.8 will be pretty long, pretty close to the actual value. So it'll be somewhere about that length right there. So will that touch the other side? Well, let's see. I mean, if we pull this down, it looks like, yeah, if I allow this to touch the other side, then that length right there might in fact be 22.9 or 22.8. But you might also notice that it's possible for that side to come out this way as well, be the exact same length, except now I might have two potential solutions. So we're not real sure whether or not it's going to be side A here or side A here. So this is where we're going to have to actually do the law of sines to figure this out. So let's write out that the law of sines says sine of angle A, or sine of 55.3 degrees, over its opposite side, which is 22.8, is equal to sine of angle B, which we don't know, over its opposite side, which is side B. Keep in mind, we also know side B and side B is going to be 24.9. So notice the only unknown again is going to be our angle, in this case of B. Now let's look where B is though. B is either opposite side B, which means it could be this angle, but then it might actually be the larger triangle, and therefore this might be side B over here, or angle B over here. The problem is, based on our diagram, we're not sure. And so I know that sometimes it's a little tough to be able to tell when we're going to have two situations. So let's go through the law of sines and the actual algebra to determine why we might have two solutions here. So we start by cross multiplying. We get 22.8 times sine of angle B is equal to 24.9 times sine of 55.3 degrees. So when we divide by 22.8, we get that sine of B is equal to 24.9 times sine of 55.3 degrees. And now we're dividing by 22.8. When we evaluate this ratio on our calculator, we get about 0.897868. And when we take sine inverse to find what that angle is, we know that there is a possibility of getting this value because it's less than 1. And so notice that we get an angle of approximately 63.9 degrees. So let's take a look at what that means on our graph. If I look at 63.9 degrees, somewhere about like this angle, somewhere around there, notice that sine of angle B is saying that there is a y coordinate of 0.89. 0.89 or so. But keep in mind that based on the fact that sine of angle B was positive, doesn't that mean that there's actually another angle in the second quadrant that could make this true? So what we need to do is recognize that B1 is this angle right down here, 63.9, because of the fact that it's an acute angle. But let's just call that B1 because it turns out that there's another angle called B2 that's going to be the corresponding obtuse angle right over here. And the reason this is true is if side A and side A are both two sides or the two legs of this triangle, then notice this triangle on the right side is actually an obtuse angle. I'm sorry, is actually an isosceles triangle, which means that the angle on the other side is equal to B, which means by the law of supplementary angles, we're going to be able to find what B2 is by simply subtracting that from 180. So if I say 180 degrees minus 63.9 degrees, notice that there's a potential of having a second answer, and it looks like there is. B2 is 116.1 degrees. So when we come over here, we've got a potential angle of 116.1 degrees. And therefore, that means that we already have two separate triangles. We know one triangle is still going to have side B and angle A, and it's also going to have the value of A being 22.8, but there's two different triangles that could be solved here. This thin obtuse triangle, because it's got an obtuse angle, or the larger acute angle still satisfies the same exact information. So at this point, it can help to make a little list of what we're trying to do. We should first of all recognize that angle A, and side B were already given, which means we need to find angle B, angle C, and side C. But we've just determined here that there's two potential triangles. So let's just keep a list of B1, C1, and little c1. And then let's keep a list of B2, which I should label over here as B2, C2, and little c2. So we already know a couple of these values. We know that the acute angle could be 63.9 degrees, while the obtuse, the corresponding obtuse angle would be 116.1 degrees. So why don't we start off by finding this triangle over here. Okay. In other words, let's go ahead and shade that piece. And so this is the triangle we're going to start by finding. Okay. Well, that means that we're going to need to find this angle right up here, which is going to be our C2. So notice the way we could do that is subtract from 180. So we have 180 degrees minus the sum of 116 degrees, or 116.1 degrees, and 55.3 degrees. Now we would know at this point if there was a second solution, because it's possible that we get the acute angle and its corresponding obtuse angle, but then when we add these two angles together, that exceeds 180 degrees, which means that it couldn't be a second triangle, so it would only be the larger of the two. And so in this case right here, we find out that our C2, by adding each of these, okay, is going to give me a value of 8.6 degrees. Okay, which means that C2 is 8.6 degrees. Very thin angle, but sure enough, a second triangle nonetheless. So I know that this angle up here is 8.6 degrees. And so now that we have each of these values, we know that side A is going to be 22.8. Notice that we have 5 pieces of our triangle at this point. So why don't we now use the law of sines in order to find the missing side, side C. Okay, so this gives me sine of C2, which is 8.6 degrees, over its opposite side, which is C2. Let's look where C2 is. C2 is this side right down here, this side of the triangle. So it can definitely help to draw this diagram each time just so you could keep track of what we're finding through the law of sines. And then we're going to use the full ratio that was given in the problem. So we're going to use angle A and side A. So we're going to say sine of 55.3 degrees over 22.8. Okay. We can now cross multiply to get C2 times sine of 55.3. And that's equal to 22.8 times sine of 8.6 degrees. And so we could divide in order to get 22.8 sine of 8.6 divided by sine of 55.3. And now we could find out that our C2, when we use our calculator here, is going to be 4.15 feet. Now that's pretty small in comparison to 24 feet and 22 feet. But that makes sense because if we come over here to this short side, it should be significantly shorter than the other two sides anyway. So what we've done is we've already found our whole second triangle. But we still need to find C1 or the angle C1 and the longer C1 or the length C1 for the larger triangle. So now let's take a look at the larger triangle, which is going to be the entire triangle. Okay, so if we have this situation now we've got to find out where is C, right? So now angle C is the full angle right here, that would be C1. And if I have C1 there, then that must mean that this entire length is going to be the length of C1. And so we could find that simply by using the law of sines instead of using this angle. Okay, we're going to be able to now use this angle. All right, so let's set up another law of sines. Okay, so in order to first of all find C1, okay, C1, the angle, is equal to 180 degrees minus this angle and this angle, which are the original angle A and the acute angle for side B, or angle B. So we have 55.3 degrees plus 63.9 degrees. Okay, which means that angle C1 is going to have the value of 60.8 degrees. So we can now come up here and recognize that that whole angle is 60.8 degrees. Which means the only thing we have left to do is redo our law of sines in order to find our last side. Okay, so there's C1. And so now for C2, or I'm sorry, for length C1, we'll say sine of angle A, which is 55.3 degrees, over its opposite side, which is 22.8 feet. And that's going to be equal to sine of this new angle, 60.8 degrees, over its opposite side. And now we're calling that opposite side C1. Okay, so we know that C1 is 60.8 degrees. All right. And if we end up working through the actual algebra by cross multiplying, we would find that C1 is 24.2 feet. Okay, and that means that we filled in the rest of our triangle. So the reason this is called the ambiguous case is obviously because it's unclear whether right at the beginning, by being given this information of a side, another side, and an angle, the reason this information is ambiguous is because in one situation, the opposite side was way too short to ever reach the other side. In another situation, the side was long enough to reach the other side, but it could have come back towards angle A, or it could have come away from angle A. And so there were two completely different triangles here, which we needed to account for separately. So let's look at one more situation, just so we could see one last scenario. I'd like to do this example, without drawing a triangle. Just by using the law of sines, how can we determine how many triangles we actually have? So let's keep in mind the given information here. I'm given angle A and its opposite side, and then some other random side C. So let's start by filling in the law of sines here, which is sine of 43.5 degrees over its opposite side, which is 10.7. That's equal to sine of angle C over its opposite side of 7.2. So if we want to isolate sine of angle C, notice that sine of angle C, if I just multiply both sides by 7.2, becomes 7.2 sine of 43.5 degrees divided by 10.7. And so in this scenario, we find that sine of angle C is equal to the ratio of 0.463198186 or so. Okay, so some decimal approximately 0.46, which again is possible because of the fact that it's less than 1. But it also means that there's two potential angles for angle C. Let's just go ahead and work through this and see that angle C Okay, we would see that angle C is going to be 27.6 degrees. Okay, well, if angle C is 27.6, it's also possible that C2 could be the supplementary angle to there. Because notice that if we have on our diagram 27.6 gives me this y value, then the angle of 27.6 into the second quadrant would give me the same y value. And so notice that if we subtract that from 180 degrees, we get 152.4 degrees. And so again, it does look like there's a potential for two different triangles, C1 and C2. So while we're at it then, let's just go ahead and use that information to find angle B. So we'll call it B1. Now keep in mind that B1 is just 180 degrees minus, well, 43.5 degrees, which was given, and 27.6 degrees, which was also given. And so that means that B1 would have to equal B1 would have to equal 108.9 degrees. Okay. So we've got the angles inside of the first triangle. So let's go ahead and go over to this one and find angle B2. Now angle B2 is going to be, again, using angle A, angle C, and then finding angle B. So we've got 180 degrees minus the sum of 152.4 plus 43.5 degrees. And therefore, we've got that B2 is equal to 180 degrees minus, and now if I add these together, I am subtracting 195.9. Which means that if there was a second triangle, B2 would have to be negative 15.9 degrees. And that makes no sense. So notice that this is a scenario whether we thought that there might be two triangles, and because the second triangle, the obtuse angle, was too big in order to make another angle, it turns out that there are not two triangles. We know now that there is only one solution. So we still have to go through this process of trying to determine if there was a second solution, but it turns out now that none of this work over here actually yielded a second solution. So we're only going to deal with the information that we already have, which means the last piece of information we need is the side B, okay? So we could go back here. We don't really need the subscripts for these anymore because there is only one solution. So let's use our law of sines again, using the information we originally had. That's sine of 43.5 degrees over its opposite side of 10.7 is equal to sine of angle B, which is the other angle that we just found, divided by side B, which is the last side that we need. So if we cross multiply and solve, we get 10.7 sine of 108.9 degrees equals B times sine of 43.5. So if I want to solve for B, then I divide by sine of 43.5. Okay, so the last side then, side B, we know is going to be 14.7 inches if we punch that into our calculator, and therefore we have all of the information. Okay, so let's just keep in mind that all of this highlighted in blue here does not yield, it's not saying that we don't need to do that work because we didn't know whether there were going to be two triangles until we did the work. But now we should recognize that we have only one triangle. So let's take a look at what that looks like. So we saw that angle A, or side A, was longer than the other side that was given. So we know that if side C is 7.2 inches and side A is 10.7, that means that it is definitely going to hit the other side. Okay. However, we need to recognize that it was long enough to hit the other side, but it was longer than 7.2, which means that there was no way for me to come back towards angle A in order to hit that opposite side. So that's why the only thing I'm able to do is go away from angle A, which is why that side is much larger. And so now, based on the information we found that angle C was equal to 27.6 degrees. And we found that angle B up here was obtuse. It was 108.9 degrees. And so we know that the longest side is opposite the longest angle, or the largest angle, which is why we know that side B is what we just found as 14.7, which is over twice as long as the original side given. And so this is a situation, the ambiguous case, anytime you're given an angle and its opposite side with some other random side, we need to recognize that there's always a possibility that you either have no solutions, if that opposite side is too short, two solutions, as we saw in this problem here, if it's long enough to hit the other side, but it could come back or forward, or one triangle if we recognize that, if we recognize that in finding that second angle, it's larger than 180 degrees.